Okay, good morning, everyone. Nice to see you. This is class number 5. It's called Two Mysteries. And I'm going to give you the bottom line is at the end of the class, I will not have resolved either of the two mysteries. So it's just the mysteries. But well, this isn't working. Let's see what's going on. And I think one of the nice things about astronomy, and as well as other fields, is that, but in astronomy, it's pretty easy to bring people up to current research and current issues that we're dealing with. They're not so hard to understand what people are grappling with. And I think that's the case in both things today. So the mystery number 1 is dark matter. We'll talk about clusters, some early work by an interesting guy named Zwicky, galaxy rotation, and attempts to identify this dark matter. And then in the second part of the talk, we'll talk about dark energy, which is a newer mystery. First came up in the late 1990s, and it came out of attempts to test the expanding universe ideas, which we talked about in the second talk. So that's where we're going today. And mystery number 1 is dark matter. And it came about in this way in the early 1930s, a long time ago, now almost 100 years ago, actually. And remember that galaxies cluster. They form big groups. And some of these groups are thousands of galaxies. So they're the biggest things that we know in the universe. This is the Virgo cluster, which is a very rich cluster. And we're at the outskirts of this cluster and probably gravitationally affected by the masses of the galaxies and objects in this cluster. But it's pretty complicated. And here's another one, the Coma cluster. The M87 is either this one or this one now. I think it's this one.
It's the right one.
It's this one?
Yeah.
You know that? Okay, cool. And that's where that giant black hole is, which I showed pictures of. But anyway, it's another very, very rich cluster. And in the 1930s, people started looking at these galaxies because they're in fact moving. Right? Everything is moving. And I'm not talking now about the universal expansion. I'm talking about moving with respect to each other. They're in their gravitational fields with respect to each other. So they move around. And they move something like this. I mean, I made this up. That's not actual motions, but that's the kind of motions that you expect. The cluster is held together, and these things move around under the gravitational attraction of all the other galaxies. Okay, so it's a little slightly more complicated than in our solar system. We know in our solar system, the planets move primarily under the interaction of the gravity of the sun, because the sun is a vastly bigger thing. There are measurable changes though because of other planets. The Earth is affected by Jupiter, for example. But here there's no. Although the center galaxies are there's more of them in the center of the cluster and they're more massive, but basically it's a spread out thing. And so I imagine it's like a cluster of gnats all flying around, and they're attracted to each other, but not by gravity. Okay, but that'll make some whoopee or something. But anyway, that's how you can imagine the cluster, the galaxies in a cluster. And what Fritz Zwicky did, he worked out the dynamics of this. He worked out, well, if they're all moving under the effect of gravity, how much gravity is there? And he did this carefully for a number of clusters in 1932, and he found there wasn't enough gravity. If you added up estimate the masses of all the galaxies you see, then there isn't enough to hold the cluster together. But the cluster is being held together. So, and the discrepancy he found wasn't small. he found that if you add up all the mass of the galaxies, that's not nearly enough to hold the cluster together. You need 6 times as much mass, approximately, as what you see. And so Zwicky proposed that there was a lot of matter in that cluster somehow that we're not seeing. Now that's surprising in a way, but it's not totally surprising, because there's no reason why everything in the galaxy in the universe should be bright as stars and galaxies that we see everything. There could be lots of stuff that's dark, right? So it's not necessary that everything is totally illuminated and bright. So Zwicky proposed that there's dark matter holding these clusters together. And this is a real thing, because, for example, if the Earth were a totally cloud-covered planet, always cloudy like Venus, we would still know there's a moon out there, because we could determine it from the tides. Yes, we would know there's a moon out there because of the tides. And so it's an indirect measurement that there is something out there with mass. And that's the way that we have with the dark matter in galaxies. Okay, I see a couple of questions.
How were they able to measure the mass of a galaxy in 1930s that's just at the edge of what a telescope could see at the time?
Well, because it's an average thing. It's an estimate, right? The galaxies look like our galaxy. We know the mass of our galaxy, 200 billion suns. Andromeda is 300 billion suns. So we know the range, and so you can add them up that way. It's an estimate.
Is there any way to actually measure any velocity of a distant galaxy except along the line of sight?
No, you measure the line of sight velocities. Okay. But you know, if you see the line of sight velocity, the velocity perpendicular to you is approximately that same amount, right? I mean, galaxies don't just go in one direction only, right? They're moving around. Okay, well, Zwicky, I just should mention the thing. He was an interesting guy, a Swiss astronomer, came to the United States. He and Walter Baade, his a co-worker, they came up in the 1930s with stuff that we're talking about today, with dark matter, with supernova was their idea, neutron stars. 100 years almost before they really became there. And the dark matter idea wasn't lost, but nobody knew how to approach it. And I remember in grad school, people said there is this question of what's holding these clusters together, but we don't know what it is. And Zwicky had proposed this, but it wasn't an active field of astronomy until the 1970s. And one of the reasons might be Zwicky was one of these strange astronomers, somewhat quite strange. He got into these huge fights with people, not just arguments, but they were true fights. And to the point where that people got scared of it. And and he was constantly he did this famous work with Walter Baade, and then about 10 years later, Baade wouldn't go near in the same room with him anymore. I mean, it was, but an interesting thing about this was another story I heard, that Jesse Greenstein, who was the director of the observatory, people asked him, how can you stand Zwicky? And Greenstein said, well, some of Zwicky's crazy ideas might turn out to be right. So he had that kind of vision. All right, well, that's where the situation was until about 1970, when several astronomers, Jan Oort and others, but primarily Vera Rubin and Kenneth Ford, attacked this problem from a different point of view. And what they did was they looked at spiral galaxies, and their initial idea was these galaxies are rotating, things are moving around in them, but how does that really work? Remember, in the first lecture, I think I said our sun and our Earth go around our galaxy once in 230 million years. That's the rotation rate. And but how does that really work? So they did detailed work on the speeds of stars and galaxies. So a typical orbit might be this, right? A star circles like this, and it would take about 230 million years to go around, but they could measure those velocities. And they found something very odd. These stars are going too fast. Because you can do the same kind of an argument that this star must be moving. You can imagine it like a planet, like the Earth going around the sun. Now, the matter is not all concentrated in the center, but a lot of it is there. So it's not quite as simple as the solar system, but it's approximately that way. Let's do it. Yeah, here's a picture of it. Here's a picture of the solar system, how the solar system works. We have the sun and the planets going around it, and on this graph, I have the orbital velocity on the vertical axis, and the distance from the sun is on the horizontal axis. So it's the further you get from the sun, the slower it moves. So Pluto is P, it moves the slowest. Mercury is closest to the sun, M at the top, and it moves fastest. And that curve is the Kepler curve. This is what Johannes Kepler worked out in 1610. Okay, and it's very accurate, and it exactly accounts for things.
Question,
Yes?
does the Newtonian formula for gravitational attraction work with general relativity?
There's a slight correction from general relativity. And in fact, that was the first test of general relativity. Mercury is an slightly elliptical orbit, and that ellipse precesses, and it's about 2 seconds of arc per century or something like that. I mean, a very small amount, but nobody could ever understand that until Einstein did general relativity and found that correction. So general relativity didn't overturn Newton's work in the sense of, I mean, it did overturn it conceptually, but all that Newtonian stuff is still very valid. That's basically what we use for most of the space travel and so on.
It's not enough to explain the too fast motion you were describing, or the dark matter, the attraction that holds
No,
the galaxies together.
No. Okay, so the point is these things are going too fast. And here's a famous curve that Rubin and Ford came up with. We're plotting again the speed, and now the distance from the center of the galaxy. So it's like the previous curve. And if it were moving the way we expected, it would be this graph here, right? It falls off with distance. The further you get from the center, they'll be going slower. But in fact, what was really found was they're going level or faster, the opposite. So that was an unexpected result. This is a famous graph that they're trying to plot here. This is the center of a galaxy, it's superimposed here. And then the further out you get, the slower the stars are moving. And what you don't kind of see here is that galaxies are really bigger. If you take longer and longer exposures, you see galaxy stuff out here, but it's overexposed. So there's well, how can you explain that? Well, you can explain it with mass. Here, let me now show the nice thing I got. This is the left is these are mathematical approximations. This is what you would expect, what was expected, that the stars out here would be moving slower than the stars in here. And this is what was observed. Didn't work. It's not working either. What's going on? There we go. Okay. So on the left, you see these are moving pretty slowly compared to the center. Here they're moving much faster. That's what was observed. The other interesting thing to see about this is that it's you see the pattern. The stars rotate differently from the pattern. Right, the pattern didn't rotate as fast. The stars actually rotate around, they go through the spiral arm, slow down, and then continue on. And then as they may go around, but then the pattern itself rotates, but more slowly than the stars. So it's kind of complicated. That's the way nature is. So this is what is observed and couldn't be understood in terms of the simple gravitation, the mass here. And the amount of mass that you needed to make this work was about 6 times as what you see.
Roger, I'm sorry, could there be more other forces like electromagnetic forces at work? There are hot plasma flying around all over the place perhaps?
Well, nobody's ever come up with anything that would work, okay? Electromagnetic forces tend not to work in this kind of a thing because they balance each other out. New charges, you know, if you have a negative charge, give the force, you attracts positive charges and then there's no force. Okay, now, it's a good idea, but not quite. See it again.
Could the center of stars be much denser than?
I appreciate your questions, but it's going to be hard for me to respond to all your theories in the class. And I would suggest if you have theories to solve this and the dark matter problem too, you think about it and write a paper, okay? And then I'll do that, okay? All right. I don't mean to do this to your class.
No, I understand.
Okay. Okay, so we've got to have dark. There's more matter that we're not seeing in order to make this work. And that corroborated what Zwicky had done many years earlier. So here, the idea is, and maybe by this time you got it, but if you rotate faster in a carousel like this, then the kid has to hold on more tightly, right? Or be thrown off. And the force there is how hard he holds on. But the force in a galaxy is the gravitational force. And to get more gravitational force, you have to have more mass. Because the more mass you have, the more gravity force you have. And so this is what we think happens. You see the visible galaxy, and then in order to get high speeds out here, this dark mass can't just be located with the galaxy, but has to be in a big halo, what we call a halo that surrounds the galaxy, which is much bigger than the galaxy. Okay, so this is how we think the dark matter is distributed, and the visible matter is small like this. So this is slightly into Skidoo. People are trying to measure these halos, and you know it's a difficult business. Okay, so for a galaxy, again, you see this, and you have to imagine there's dark matter that you're not seeing that extends way beyond what you're seeing here in the photograph.
Roger, can I ask a question?
Yeah.
So the stars are made up of dust and things that are floating around. They're not illuminated. It's just dark, and then gravity pulls them together, and a reaction occurs, and they become illuminated. Is that right? Is that the difference?
Yeah.
So is the dust the dark matter?
No, it turns out that dark matter cannot be made of things like protons and neutrons, which dust and we are made of. And the reason for that is if there were 6 times as many protons and neutrons, then in the early universe, when helium was formed, which we talked about last time, that would be all wrong. We wouldn't have 29% helium or as we do now. That would throw that off. So that we already know the dark matter, which is 6 times the normal matter, can't be normal matter like us. Has to be something more exotic. Okay, so a way to think about this. This is the halo, and some of them may have dark matter halos, but I kind of doubt it. Anyways. The way to remember it, okay? Yeah, I didn't remember this. Yeah. Okay, I just say a couple of things about Vera Rubin. She's a very capable astronomer. I met her a couple of times, but just casually. She did do work for women, and this is the famous curve that she and Thompson derived. So he did actually the building of the instruments, and she did more of the astronomy and interpretation of the results. And you know, women didn't get enough credit, but now the pendulum has almost swung a little too far. She gets all the credit, but she couldn't have done it without the instruments that he built. So, okay, yes.
I was, a few slides back, you said, it said something about 21 centimeters through hydrogen or.
Yeah.
through hydrogen.
Yeah.
What
What is that? From the far out galaxies, hydrogen is the gas that's most predominant. And a lot of hydrogen exists between the stars. It never forms stars. And that is an easy gas to measure. And you can measure its velocity at high distances, far distances. Okay, one of the things that are happening is a new telescope is just coming online called the Vera Rubin Observatory. And it's a big telescope, about 8 meters in diameter. Yeah. And its function will be to map hundreds of millions, billions of objects every 3 days in the universe. The whole sky that it can see will be mapped every 3 days. And then we will see changes. We'll see supernova exploding when they explode. We'll see nova when they go off. We'll see gamma ray bursts, all kinds of stuff, neutron stars colliding. It'll be a tremendously game-changing thing. It's down in Cerro Tololo in Chile, Cerro Pachon in Chile. We have a big observatory in Cerro Tololo too. The 2 best sites known on the planet for astronomy are Mauna Kea in Hawaii and the Andean Mountains in Chile. So if you're going to build a big telescope, you should build it in one of those 2 places. Okay, so what is it? This is, I tried to summarize this. It couldn't be protons and neutrons because the question you asked. It also can't be dark stars or black holes because black holes are made out of neutrons and protons, at least the ones we know. And that would mess up what we know about the universe. So people think it's more exotic particles. I just mentioned 2, but there's lots of theories. And one is called weakly interacting massive particles, WIMPs. And the idea there is that the dark matter clearly doesn't interact much with ordinary matter, except for gravity. That's the only way we know that it really interacts with anything. And it doesn't have many strong forces with our ordinary matter. Otherwise, we would detect it. And so one of the ideas was, well, it doesn't interact much, but there's the weak force. I haven't talked much about that, but there's a very weak force in the nucleus, which gives us electron decay. And maybe it's that. And that was a very popular idea for the last 40 years. And nothing has come up yet. Another idea is it's something called an axion, which is actually named after the detergent that was popular about when we were young. And that's a particle that is so weakly interacting and so small that, I'll give you an idea, a proton is about a giga electron volts, 930 MeV, billion electron volts. So 930 million electron volts. An axion is between 1 and 100th of an electron volt. So that's going to be hard to see, you know, and to detect. Well, how do we detect stuff? Well, all of these physics experiments to detect unknown particles are pretty much the same. You crash 2 of them into each other and see what comes out. So, okay. So that's the idea. That's how you do an experiment. Some physicists say all physics experiments are this way, but let's see, okay. And lots of things have been tried. Well, here's a cloud chamber photograph of this kind of a thing happening. You see it. There's a particle that's come in here and then it's hit something and other particles have come out. And they do all this kind of stuff and there's complicated stuff's happening. So obviously a bunch of particles came out in this initial collision and then subsequent decays and collisions happen. Grad students spend all their lives interpreting these things. Pardon? It's a photograph. Okay, well, one way to do this, some of these experiments, was the WIMP experiment, is to shield it because these interactions are going to be so weak. Every other kind of particle, cosmic ray and stuff, is going to interfere with it. So one way to reduce that interference is to go deeply in shielded places. This is an old gold mine, which is underground. And there they have a big xenon detector. And the idea is that even though it's very, very, very rare, every once in a while, a dark matter particle will collide with a xenon. And xenon is for technical reasons, and we'll be able to detect that. And they have been working for a long time, but no definitive results yet. That's the kind of experiments that are done. Another one is with a collider. This is a large hadron collider outside of Geneva, 16 miles around. And it blasts particles at very high energies into each other. This goes all the way around to 16 kilometers, and there's high particles go in here. They come at extremely high energies, and the beam is pretty intense. If ever the beam got loose from this thing, it would go through about, I don't know, several hundred meters of rock and so on. You don't want to stand in the way. And here's a collision, and you can see it's pretty complicated. It's two protons colliding with each other. Proton and antiproton, they collide with each other. Protons are complicated particles and lots of things come off. And the idea for dark matter would be, since dark matter doesn't interact, it wouldn't even make the light, but if we add up all the energy of the initial particles that come out and all their masses and all their energies, and then the collision, and after that, add up all the energies of all of this stuff, their masses, they should agree. If they don't agree, that's indications for dark matter. There's something we're not seeing. But so far, no light. We keep, every once in a while in the news, you do hear about, they think they've seen one, but when you see one example, that's not enough, it's got to be reproducible. That's okay. So, and yet another way to detect dark matter, and this is a very good way to do things. It doesn't identify what the particles are, but it tells us something about it. Is if you look at this is a JWST observation, and you see a lot of stars and galaxies, but you also see these things, these arcs. And what's happening here is something kind of neat, that light having energy is attracted by gravity. And that was the sort of the second test of general relativity after Einstein proposed it. They saw that light passing near the sun during eclipse, say, when you can see the starlight, is bent a little bit. Just like if you were attracted to something. And this is what happens is you have a distant galaxy, then you have a big cluster of galaxies with dark matter. And although the light from the distant galaxies first expands, the rays go out the way it normally does, but then they're focused again by this mass. And we see that effect. That's what causes those arcs. That's a distant galaxy with its light distorted by passing near a cluster. And here's a good one, I think. This is a really good one. Most of them aren't this easy to interpret. This is from a distant galaxy, which is focused by this object here.
Nice.
That's about the best example. Most of them aren't this neat, but and so now that is a way to measure the mass and the extent of the dark matter in this cluster. So that's a good way we have of measuring the dark, telling us more about the dark matter. Okay, well, this graph is a little bit. I'm going to talk about dark energy later, but here's the. If you look at what's in the universe, then all the stars and planets that we see are about 1/2 the mass of the universe. There's a lot more. I've talked about this. There's a lot of gas between the galaxies that's never formed stars or galaxies, and that forms about the two together form about 4%. And then there's all this dark matter. So you see, all the stuff, all of astronomy is just a sixth of what's out there, of the mass that's out there. And that it doesn't even talk about the dark energy yet. So that's sort of sobering, right? And and I've talked about what is the dark matter, but maybe it's 100 different things, right? Maybe it doesn't have to just be one thing. So there's a whole thing here that we've got to try to understand. Okay, so so summarizing this, so there's nothing definite yet from the laboratory experiments. And this has been going on for a long time, right? For 40 years have been for these laboratory experiments. There are enormous efforts to identify it. It's a critical question for astronomy, but it's also a critical question for physics. If there are physics tries to understand the basic ideas of matter, neutrons, protons, quarks, electrons. But if there's a whole big family of other particles they're not seeing yet, then our physics is incomplete. So it's a critical question for physics as well. Dark matter plays a fundamental role in the formation and evolution of galaxies. And that should be rather obvious, right? If there's 6 times as much matter in a galaxy of dark matter as visible matter, that must have a lot to do with how the galaxy moves, evolves, and changes, and so on. So it's critical for astronomy as well. And but one of the things that I've heard talk about lately is if dark matter doesn't interact at all with normal matter. See, with the WIMPs and the axions, we were hoping there was a little bit of interaction with ordinary matter. But if it doesn't act at all with ordinary matter, and if it's only subject to gravity, then it's really going to be hard to do in the lab, because the gravity in the lab is tiny compared to anything else. Okay, so that's where we are here. That's a mystery. And I'm sorry, I can't tell you more. That's where we're working on it. Okay, so let's take a break.
Well, let me say that, we are recording all of these, and normally we post them on YouTube, but Dennis Morris does it, and he's in Australia. If you want to see the last 2 or today, just send me an email, B. Bowman, and I can send you the link to the recording. And then in a week or so, we hope to have everything up on the site.
Okay, thank you. Cool. All right, let's take a break. Okay. Everybody, we're about to start. My name is Doug Garcia, and I just want to spend a few minutes. I would like to acknowledge Jim Green, who is our newest volunteer member for the Zoom. The Jim has taken over, by the horn, and he's doing it all today. Any other volunteer positions? Let me know, or write to OLLI. Thank you. Maybe it's a good time to acknowledge the Zoom team also, Barry and Doug, and Mark and Jim. That's good. They're really doing a lot. They're coming to every talk. They're setting up, and each time before the talk, it looks like it's not going to work, and they make it work. So it's really cool. Okay, thank you very much. Okay, let me now talk about dark energy. Another mystery. Here is a Hubble diagram. We talked about this in the second lecture. And we'll talk about this quite a bit today. The point is that when we measure distant galaxies, each point on this graph is a galaxy. And we measure its distance and its velocity. Then we find that the further out we go, the faster they go. And that we showed that was just a natural result of expansion of the universe. And it makes a beautiful straight line. The original Hubble data was just in this little red square here, but since then we've extended it for huge distances. But now I want to now, I'm a little out of order here. But let me do it this way. I now want to talk about supernovae again briefly, because we're really going to use those to learn something interesting about the universe. Supernova is an exploding star. We had one in our galaxy in Magellan Cloud in 1987, and that was the before event, and this is the after event. The star exploded. Some stars do that. Massive stars explode. And that's called a supernova. And here's another one in a very distant galaxy. This is the before picture on top, and the supernova picture on the bottom. Now, the thing that's you need to look at here is that when that star in that galaxy exploded, it was bright like this for a few weeks, But look at its brightness is comparable to all the other stars put together in that galaxy. And there may be 200 billion stars. So when one of these things goes off, it's no joke. I mean,
well, you know a joke though, don't you?
yeah. Well, I think I gave this example before, but roughly, an awful explosion is a hydrogen bomb, and the way it gets its energy is it converts some mass into energy, and the amount of mass that a hydrogen bomb compares is a few teaspoonsful of mass. It's lots of energy and a little bit of mass, a few teaspoonsful. But when a supernova goes off, it converts a third of the mass of a whole star into energy in a second, fraction of a second. So that's what happens. But the neat thing about the supernovae is that we can see them a long way away because they're so bright. And that means we can see them from very far away. And here's a couple of remnants, what happens afterwards. That's really not relevant to what I'm talking about, but they're fun to look at. This supernova was actually seen by Tycho Brahe in the 1570s. And we see the pieces of it today. Now, I'm going to skip over something fairly complicated. But what happens in there are different types of supernovae. And what happens in the interesting ones that we're going to talk about is that you have a late type star called a white dwarf often. And the white dwarf star have one property. They can be stable up until a certain mass. But if you exceed that mass, the whole thing breaks apart and explodes. And what happens in nature is that you get a white dwarf as part of a binary star. There's a normal star and a white dwarf next to each other. And the white dwarf, if they're close enough, the white dwarf can draw matter from the normal star and then exceed that critical point. But they all explode when they exceed that one critical point, which means they have all the same mass, which means that the luminosity is always the same. Okay, and that's what we call the standard candle. Remember, we used the Cepheids as a standard candle because we knew how bright they were. But now the supernova, we also know this type of supernova, we also know how bright it is. Okay, now that's all been very carefully measured and calibrated, and there's some exceptions, and nature is not simple at this level, but it can be understood. Okay. So now we have two things. We have something very bright. We have something we know how bright it is. That means we know how far away it is. And so we can use it to recalibrate the Hubble relationship. Okay. So this idea became clear in the 1980s and 90s. And the idea was, even at that time, remember this graph that we look at how the universe is expanded. The A, the vertical axis, is just the distance between two typical galaxies. And if the whole universe is expanding the same way, then it doesn't matter which ones we pick. And this is time. And the Friedman and others calculated that what could happen in the universe is it could first expand and then stop and then contract again, just like you throw something up and it comes back down, or it could go up and expand forever. Just like a rocket could leave the Earth, and here's the intermediate place. And so in the 1980s and 90s, the question was, well, which universe are we in? And to do that, you clearly have to measure these velocities, and two teams decided to try this, to measure very distant supernovae, to calibrate the Hubble constant, which would tell us whether the universe was going to expand forever or whether it was going to come back again. So which one of those curves? One was a UC Berkeley team with many partners, and the other was a Harvard team with many other partners. So they were both working on the same problem. Harvard is an Eastern college that tries to keep up with Berkeley. Okay. And I'm sure nobody hears from Harvard because you would probably be jumping. Oh, there you go.
No.
Okay.
No, UCLA.
Okay. All right.
I have a question. You mentioned that, you see the explosion for several weeks.
Yeah.
Why it's so long?
It's a huge explosion. The explosion doesn't take very long, but it illuminates these gases and they take a while to cool. Okay. So they decided to look for distant supernovae. Now, this was a very difficult experiment. Not all the supernovae are all that bright. Here's one you can see there. Okay, see how it got brighter, but it's obviously a little more difficult problem. Here's another couple you can barely see. So it wasn't an easy experiments to do. And what was also difficult is you can't predict when a supernova will go off in a galaxy. Roughly, they go off one every 30 years in a galaxy like ours, but you don't know which one or where or when. And so but in order to do this experiment, they needed big telescope time. They couldn't go to the biggest telescopes on Earth and say, well, give us time and maybe a supernova will come off and maybe we'll see it. That would not work. So what they did instead was use smaller telescopes and automatically constantly scan the sky for supernova. And did it every single night, every clear night they had, and kept going for supernovae and scanned a big part of the sky. And then they could come up with a statistic that says, well, if we look for supernovae for 3 days, we'll probably see 4 or 5 supernovae during that time. Okay. And with the small telescopes, we'll know exactly where they are. So give us the time, and we will keep doing this. Give us 4 nights. And although we don't know which supernova we'll see, we will see 4 or 5, and then we'll immediately turn the telescope to that and we'll measure it. So and as you can kind of imagine, that's easier to describe than it is to do. I mean, you have to organize the telescopes and the observers and the instruments and all this stuff. So a big effort. And they made a shocking discovery. They got the velocities and the distances, but they saw that the distant galaxies are moving slower than the near ones. Okay, see, if the universe were slowing down, it'd be the other way around. The distant ones would be faster. It is speeding up. Really strange. So here's here, I think this is a qualitative graph. I got this off the web. But if you measure the velocity versus distance, then when you go to very great distances, it begins to deviate from that straight line. Okay, they're going too slow. And that's what they found. So let's see, I think I try to make an animation of this. Oh yeah, okay. See now, if you imagine the universe expanding, and we are of that galaxy in the corner, and we're looking at light from distant galaxies. Okay. Now, what happens as the universe expands, light comes in, and then when we see light from a nearby one and a distant one, the distant one left earlier, right? You see it? So we're looking back in time, and we're looking at an earlier part of the universe. That didn't come out so great, but again. All right, so what they found, which was it? It wasn't any of them. It was this. Oh no! I wrecked all the drama. So try it again. Yes.
Hey,
All right.
I'm shocked.
That's a heuristic way of looking at it. The universe is speeding up. That was very unexpected. Okay, so what causes the acceleration? That we don't know. And we've given it a name called dark energy. But that doesn't mean we understand it, right? That is just a name for what we don't understand. And so, oh yeah, scientists were stunned by the discovery of the accelerated universe. That was sort of true, but we're always being stunned. I kept hearing this. Astronomers stunned by discovery of mysterious filament. Black hole stuns astronomers. Scientists stunned by mysterious structures. Researchers stunned.
You're still standing.
Yeah, it's a wonder that any work gets done. These astronomers are walking around stunned all the time. So but it was a really important thing. And here's some of the.
What was this?
This was in 1997 that was published. This is one of the graphs that the early graphs, and it's a little tricky to see. There's this astronomy technology, which I'm not going to try to explain, and this one's published a little bit differently. Distance velocity. By the way, those of you who don't remember, the cat means you don't really have to try to understand this.
Will be on the test.
Right. And but you can see that the straight line. The straight line, if there were no expansion or anything, if it were just normal, it would be this line right here. But you see that it's clearly above that, which means they're not going fast enough. They're going too slow. And that is what's happening. So if the universe is accelerating, acceleration means a force, something driving it. That's what we call the dark energy. Don't worry about the splitters and stuff. Okay, so this is a strange story. Remember, Albert Einstein had proposed this lambda, which he called the cosmological constant, because at that time he thought the universe, in 1918, he thought the universe wasn't expanding or contracting, and his equations showed that it was. So he changed the equations by adding this lambda term to make it steady. And then when Hubble came along, showed the universe is expanding, Einstein dropped the lambda term, the cosmological constant. In fact, he's supposed to have said that was the biggest blunder of my life. But lambda can make the universe expand just the way it is. It could accelerate just the way it is. So we're back to Einstein's idea of the lambda. So maybe he had something, although for the wrong reasons. Okay. But that is the way we look at it now mathematically. So there was Einstein. Okay, dark energy is causing expansion of space to be going faster and faster. Dark energy dominates. I'll get to that. there's much more dark energy than there's matter. Well, that's kind of obvious, right? I mean, the matter makes it contract and the dark energy is making it expand and accelerate, and it is accelerating. So there's more energy there. And it turns out if now, getting back to this graph again, dark energy is 73% of all the energy in the universe, energy and mass in the universe. It dominates the universe. Okay. Now, the reason I can plot the energy and mass on the same graph as I did is Einstein's famous equation, E equals mc squared, that the energy and the mass are equivalent, and they're related by the energy, the mass, and c, the square of the speed of light. And that's in fact at Grace Cathedral, it's one, you can see in the window there, E equals mc squared. Okay, question?
Why do they always use C for the speed of light?
Why do they always use C for speed of? Well, I know the answer to that. When Einstein was working on the general theory of relativity, he got tired and he needed a vacation. And he decided to go down to the beach in Cancun and in Mexico. And he tried to think of some lines to pick up some girls if he could. And as he was sitting on the beach, this beautiful señorita came walking by. And he tried one of his lines. He said, do you think that the speed of light is very great? And she looked at him and she said, "Sí."
Shaggy dog around everywhere.
I think Paul Harvey in Texas made up that joke. Give him credit. All right.
Totally stunned.
Okay, everybody, we gotta get serious. That's like, oh yeah, here's another way to look at the universe. It might be easier to remember than that pie chart, okay? If you look at a piece of cake, chocolate cake, the dark energy is here. About 25% or so of dark matter, and then the stars are a little bit on top. Okay, well, I'll just say a couple more things here. We now have a theory called the lambda dark matter, cold dark matter universe. Our best pictures of the universe now incorporate this lambda term of Einstein's. We don't know if that lambda term is constant, if it varies in time, or what it does. So far, it looks like it's constant in time. And cold dark matter means that the universe was made initially, the first stars and stuff, of matter that was not relativistic. And this picture is our present picture of the universe, which explains a lot of things. Explains the helium, it explains the structure in the cosmic background, explains the evolution of galaxies. So we have a very good theory, and although we certainly don't know everything, and remember there's the Hubble tension, that the Hubble constant measured in two different ways gives slightly different answers, and we don't understand that yet. But everybody seems to think that in the future we're going to get a better understanding, but it will incorporate much of what we know now. Okay. The other thing I want to point out to you, though, is that when you look at this stuff of the universe, that's the universe today. But it wasn't always this way, right? Because the universe expanded, so things changed. And here's a graph of what kind of happened. In the first, this is years of the universe, so just 100 years here. And this is the density, how much matter there is in a cubic centimeter, right? We can't say how much matter in the whole universe because we don't know the whole universe may be infinite, but we can always say how much matter in a clump, in a small region. And early in the universe, when we had the cosmic background radiation dominated. That was the highest energy source, highest energy content in the universe. Matter was somewhat less, and dark energy was way down here. Then radiation decreased faster than the matter. And they interchanged at about 30, when the universe was about 30,000 years old, and the matter became dominant. And matter determined how the universe expanded. And this is a logarithmic curve, so these are big differences. And radiation wasn't as important, and dark energy wasn't important yet. But then matter continued to decrease, but dark energy never changes. Lambda is a constant. And so about 4 billion years ago, the dark energy became dominant. So we are now in a dark energy dominated universe, but that wasn't always the case. And that happened about 4 billion years ago. So now there's an approximation in this graph to make calculations simpler. The exact calculation is possible to do, but it's long and tedious. So this gives a good idea, but it is an approximation. But I think it's very close, actually. Does that make sense to some people? So it's also kind of interesting that, dark energy just started to dominate only 4 billion years ago, and we came along, Earth came along 4 billion years ago. Is that a coincidence? I don't know. Okay, so from this talk, to summarize things a little bit, you come away with this. There's more dark matter than ordinary matter. Dark matter dominates the formation of structure in the universe. We don't know what it is. And dark energy accelerates the universe's expansion, and it dominates the whole universe, and we don't know what it is. And so we have but even with those mysteries, we have a very successful model of the universe. We do understand a lot of what's going on, but there are still many mysteries. So that's the takeaway. Are there any questions about this?
I have a question.
Yep.
Tyson talks about negative energy. Is that the same thing as dark energy, or is that something else?
No, that's something else. Negative energy is something that comes out of well, actually, there is a way to make that come out. A negative energy term can have a pressure, and you can look at the dark energy as a pressure. And so it is related. Yeah. So my view of this is our whole look at the universe is like a few fireflies at the end of this big, dark, mysterious forest. We're seeing a few stars and so on, but it's a tiny piece of everything that's there. And there's this vast unknown in the back. So it's rather sobering, but that is our view of the universe today. Okay, that's it.
Thank you.
No, I said the end, but there is we have a little bit of time if you don't mind. There's a nice video here of Saul Perlmutter, who was the Berkeley dark energy team leader. And he explains it so succinctly and nicely that I think it's worth, I hope it comes on.
Yeah.
Oh, how can we turn up the sound somehow?
Yeah.
How do I do that?
Sure. And it becomes even more boggling when you
Oh,
talk
okay.
about something that's infinite getting bigger, expanding. So I have to try
All right,
to
let
explain
me
that.
start it
You have to
over.
imagine.
Try to start it over again.
And it's amazing that we know
Can you hear?
at all the history of the expansion of the universe. It's bizarre even to think about the universe as a whole, because as soon as you think about anything that could be infinite, your mind is boggled. And it becomes even more boggling when you talk about something that's infinite getting bigger, expanding. So I have to try to explain that you have to imagine something that's infinite, goes on forever, galaxy after galaxy after galaxy. And the only thing that's typical about it, as you see galaxies in all directions, you're in the sea of galaxies, is that there's an average distance between the galaxies. And when we say the universe is expanding, they're still all the same galaxies. It's still just as infinite. It's just that now all the distances are a little bit bigger. And so there's more space between every one of these infinite sea of galaxies. We've been using a technique, and now we've come back to it to improve it, that takes exploding stars as a distance beacon, as a standard candle, if you will. So the further away they are, the fainter they look, and that's how we tell how far they are, by how faint they've appeared. Each one of them then also tells us about this moment in history that you can tell how far back it is in time, because you know how long it takes light to reach you from that distance. And that moment in history, what we want to know is how much has the universe stretched since that time. And it turns out that we can use the colors of these very same exploding stars, the supernova, as a direct way to measure how much the universe is stretched. Since we have no idea what is causing this acceleration, we have a placeholder terminology. We call it dark energy. And the dark just refers to our ignorance, not to the color of the but what it means is that you can explain an acceleration if you can find an energy source that would actually cause the acceleration. And right now, there are a wide variety of theories that could give you that kind of energy spread throughout all of space. And that all the empty space then would be filled with this energy that can actually make space itself expand. And right now, of course, we're still completely baffled by what it is, and we're trying to develop these techniques to corner it and to sort of figure out what the properties could be that you could tell apart if you were considering these different theories. Right now, one of the biggest mysteries that we still have left is, why can we not get a single story that will make sense both for how gravity works and how all the other forces of the electromagnetic, weak and strong forces that that we understand through all the interactions of fundamental particles. And those two stories right now, have to work together. We know because the universe does it. And the question is, how can we come up with a theory that holds them all at one time? The biggest thrill would be if we were able to get a clue as to what the dark energy is, and if that ended up being the route to solving the problem of combining gravity and the other three forces. That would just be amazing.
Oh, yeah, it would be.
Okay, thank you.